Good day, grade 12 learners. Welcome to today's technical sciences lesson. My name is Musa Zulu, and this lesson is brought to you by the Gauteng Department of Education in collaboration with Saibono Discovery Center. Grade 12, today, our area of focus is going to be mechanics. We'll be doing mechanics today, paper 1 from paper 1, mechanics. And we'll be touching the topic that we couldn't touch on for term 2, which is the last topic there of term 2, work, energy, and power. A very, very big topic there with 3 concepts there that I've just underlined there. The concept being work, the concept being energy, and another concept being power. However, this topic, grade 12, you will realize, or surely you have realized by now, that it is not a tricky topic or a difficult topic. So what we're going to be doing is just unpacking some of the most important things that you need to know, and some of the things that you need to know as basics to make sure that you master this topic. It's not a difficult topic. It's actually an easy topic to get right there in your exam. All right. The objective for our lesson today is that by the end of the lesson, we expect that you must be able to define work, or define the term work done. And you must also know that work done is a scalar quantity. You would remember that in grade 10, you were introduced to vectors and scalars and the difference between the two. What do we define, or how do we define a scalar? How do we define a vector? So you must be able to define work, and you must be able to know that work is a scalar quantity. And the reason as to why we say work is a scalar quantity. You must be able to solve problems involving work done, and you must be able to do that with problems that where you are having objects moving horizontally, and you must also be able to do that when you are having objects moving vertically. So if time allows, we should be able to look at both those scenarios and see how is it that we can be able to solve those questions or those problems. You must be able to state the principle of conservation of mechanical energy. You must be able to state the principle of conservation of mechanical energy by the end of the lesson. And you must be able to solve problems again that are involving energy in one dimension. You must be able to define the term power. You must be able to define the term power. And again, you must be able to solve the problems that involve power in the context of technology. This is where we are focusing in the context of technology, as we are in a technical subject there. Okay, so pre-knowledge, knowledge that we expect that you must know at least some of these things before we get into the actual lesson. We expect that people are able to define energy. You'd remember that energy has been defined since primary school. The definition of energy. Are you able to define energy? In grade 10, again, we also defined energy. It was necessary for you to know and be able to define energy in grade 10. It was actually even examinable then. You must be able to differentiate between kinetic energy and gravitational potential energy. Know the difference between the two types of energies, especially in terms of their definitions. To say kinetic energy is defined as this, and gravitational potential energy is defined as this. And let's emphasize here on the word gravitational potential energy, not potential energy, but gravitational potential energy, because there are different types of potential energies, right? And then we must be able to define the term mechanical energy. All of these energies energy that we are talking about, these are things that were done in grade 10. You remember in grade 10, you were introduced to energy, you were introduced to kinetic energy, you were introduced to gravitational potential energy, then you were introduced to mechanical energy. So all of these we expected to know. Perhaps maybe if I were to add another thing that we would say is expected of you to bring in this lesson is the knowledge of identifying forces acting on an object, identifying forces acting on an object. You should be able to identify the forces that are acting on an object. Given an object, they say this is the object resting or moving, being pushed, being pulled, or whatever the case may be. You should be able to identify all the forces that are acting on that object. And if we are going to talk about identification of forces, then we have to bring in the issue of drawing of free body or force diagrams. Okay, so we should be able to bring this, because when we are dealing with this topic, we will also be needed to identify those forces, and for also us, it will help us to be able to draw those free body diagrams and force diagrams. It can actually be even be asked in the topic itself that we are going to be dealing with, being work, energy, and power. So let's try to look at some questions that we can ask one person to just ascertain whether they are able to answer them and they have the baseline knowledge that we expect. So question number one would be, define the term energy. I would hope that people are already writing down there that definition. And question number two would be, differentiate between kinetic energy and gravitational potential energy. While question three will be, define mechanical energy. Maybe if I can also add, just give an object here being pulled, and then I would say identify all the forces acting on the block. Identify all the forces acting on the block. If the block is being pulled here, as you can see the surface that I've indicated there, you should know the type of surface that I've indicated there and what it means about the forces that are there on that block. So just be able to define the term energy, differentiate between kinetic and gravitational potential energy, and define mechanical energy, and also try to identify all the forces that are acting on a block as it is being pulled to the right there. Okay, and if you are able to do that, or the answers that are expected of you grade 12, there will be the person would say energy is the ability to do work, or one would say energy is the capacity to do work. So both of these terms can be used. You choose one, no need for you to write both of them. You can say the ability to do work, that will be correct. You can say it's the capacity to do work, which would also be correct. The answer to question number two, which was asking you to differentiate between kinetic energy and gravitational potential energy, the expectation is that one would say kinetic energy is the energy an object has due to its movement or motion. Again, here you choose one. So you can say kinetic energy is the energy an object has due to its movement, leave it there, or you can say due to its motion. That's kinetic energy. It's the energy object has because they are moving, because they are moving. When an object is moving, is in motion, it will possess this energy. It will have the energy called kinetic energy. Okay, while gravitational potential energy is the energy an object has due to its position above the surface of the earth. This is the energy that object will possess or will have due to their position above the surface of the earth. Once the object is above, if this is our surface of the earth, the ground, if this is our surface of the earth, right? Once the object is above the surface, it will start possessing this energy called gravitational potential energy. Again, I emphasize on the word gravitational. So let's do away with calling this potential energy. I know that sometimes we take it for granted, grade 12, and then we just start calling it potential. Let's do away with that mentality. Let's call it for what it is. It's gravitational potential energy, all in full. And then the third answer there that is expected from a grade 12 learner coming from grade 10 is that mechanical energy is the sum of gravitational potential energy and kinetic energy. So when you are now adding the gravitational potential energy that we were talking about here, the energy an object has due to its position above the surface of the earth, adding it with the kinetic energy, which is the energy an object has or due to its movement there. And then my added question there, I'll simply turn it into a free body diagram just to sort of remind everyone of drawing of free body diagrams there. So I was asking people to identify all the forces that were acting on a block that was being pulled there, because I was remembering that the issue of identification of forces is also a pre-knowledge or pre-knowledge that a grade 12 learner would need. So let's identify those forces. You would have the normal force, okay, because it was on the surface, a force that is perpendicular to the surface there. You would also have the force of gravity. A force of gravity is also acting on that block. You would also have the force that was applied to the right. This is the force that was mainly responsible for it accelerating to the other side. I say mainly because it's not the only force that is responsible, okay? And then the last force, that if you look at my surface was looking like this, even though I did not state it, but by looking at the surface, you should be able to say this is a rough surface by looking at the diagram. So I'm doing this also to just sort of remind you of those things, to say sometimes the examiner will not necessarily tell you that it's a rough surface or tell you that there is friction. They'll just give you a picture with a surface that looks rough. So you should say it's a rough surface. Therefore, in a rough surface, I am expecting that I'm going to have frictional force or kinetic friction then. So this is the identification of all those forces and the drawing of the free body diagram that we might need or we will need when we tackle this topic, especially with work. Okay, so the terminology, grade 10, 12, that you would need to familiarize yourself with when it comes to this topic there is the definitions. Just know the definitions mostly. Be able to define the term work done, and it is defined as the product of the force applied on an object and the displacement in the direction of the force. We'll get into more details as to what exactly it is or what it means then. And then you must be able, at least again, these can also come as prior knowledge, because we've talked about this when we were talking momentum and the conservation of linear momentum. We talked about an isolated system, and we dealt with an isolated system in detail then, to say an isolated system is one on which the net external force acting on the system is zero. So one of the things that you must remember, and one of the terminologies that comes with this topic that we are dealing with then. And then the principle of conservation of mechanical energy. Of course, before the principle of conservation of mechanical energy, even though they are prior knowledge, even though we are coming with them from grade 10, you still need to know the definition of kinetic energy. You still need to know the definition of gravitational potential energy, and you still need to know the definition of mechanical energy. But it is assumed that now you should be familiar with them coming from the previous grade. So the terminology, the next terminology that you need to be familiar with will be principle of conservation of mechanical energy. This states that the total mechanical energy in an isolated system, you see, that's why we had to bring in the isolated system word again, because the conservation of mechanical energy happens in an isolated system, like the conservation of total linear momentum was happening in an isolated system. So we say the total mechanical energy in an isolated system remains constant. You would notice there, okay, it remains constant, okay, in an isolated system. You would notice there that in bracket, I have sum of gravitational potential energy and kinetic energy. So you can choose to state it in two different ways. The total mechanical energy in an isolated system remains constant, that's good. Or one can say the sum of gravitational potential energy and kinetic energy in an isolated system remains constant, because this is still mechanical energy. Or you can just rather choose to state the whole thing as it is coming from the examination guideline. The total mechanical energy, open bracket, sum of gravitational potential energy and kinetic energy in an isolated system remains constant. That's the one I like the most, stating the whole thing, showing that you know your stuff, you know the meaning of total mechanical energy. It's not the issue of just memorizing these things. It helps a lot when you know them. Then the last one there would be a definition of power. And we define power as the rate at which work is done or energy is expended. Okay, so you can state it as the rate at which work is done, or you can state it as the rate at which energy is expended. Okay, maybe we will look into what maybe this word means. This energy is expended there. So again, you have a choice of how to state this one, but again, I prefer that the person states the whole thing. That way, you are putting that examiner in a corner where they have no choice but to give you your 2 marks. So all remember, these are definitions. They are always 2 marks or you get nothing. So the knowledge of definition becomes important. Very, very important. Let's not take that for granted, grade 12. And then let's remember that these definitions are taken from the examination guideline. I want to emphasize this again, grade 12. We do not define according to any other source except for the examination guideline and the KEPS document. So those are the 2 sources that we use for our definition. So let's try and stick to them by all means possible. All right, so let's get into the first concept, as we have 3 concepts to deal with for today. And the first concept is work done. Okay, remember, we are just doing a revision, so we'll be focusing more on the most important things that one must know. But the first most important thing, definition. Let's be able to define work done. What is work done? We define work done as the product of the force applied on an object and the displacement in the direction of a force. Now, before I go into the mathematics, let me try and talk about the issue of work being done. So work is done on objects, grade 12. Okay, so when do we say that a work is done on an object? According to the definition, it tells us that work will be done if there was a force that is applied. That's first. There must be a force that is applied on an object, and this object must be displaced. That is very, very important. So for you to be able to identify whether work was done here, the first thing is that there must be a force, but then this force must lead to the displacement of the object. The object must be displaced. So this is very, very important, because there are times where forces are exerted on objects, but the object is not displaced. So we cannot say that work is done there. So work in this case is not the same as work in our general language, where you can stand in one place and try to push a heavy rock and push the heavy rock for the entire day while you are sweating, and then you come back, you say you were working. In this case, there was no work done in science. That means there was no work, as long as that heavy rock was not displaced. So no matter how hard you push it, no matter how big the force is, say you raise your heavy rock, you are applying this extremely huge force of 100 kilonewtons. However, the rock is just not getting displaced or being displaced. As long as the rock is not being displaced, we would say that no work was not done, or no work was done in that case. So it's very, very important that there must be a force, but then there must also be displacement. There must also be displacement. Then we can say work is done. Then the displacement must be in the direction of the what? Of the force. So it's very, very important to understand force or work done in that way. It's not similar to what we are used to in our everyday life. Or let's say it's not the same, it is similar. It is not the same, it is similar. Okay, so it's important to understand that. It's important to be able to state the definition. So I don't like people just stating definitions based on remembering and recording them. I also like people to understand that what we are talking about here is the force was there, then there was displacement. Then we say work was done in this case. Okay, right. So then from there, from that understanding of the definition itself, then we can calculate how much the force or how much work was done. So different forces will give you different magnitude of work done. Okay, and different displacement will also give you different magnitude of work done. So we can calculate and actually determine how much work was done. And we can do that through the formula which says W, and the W stands for work done is equals to F, and the F stands for the force, and the force is measured in newtons. Okay, and then delta X, and the delta X stands for what? This stands for, let me write it here, it stands for the displacement. This stands for the displacement. Okay, now before I go to the next one, let's talk about this one. This one is measured in meters, right? And then before I go to the next one, I want to remind you of the SI units that you looked at today. We have actually done work done before. Maybe you might not remember this, but in grade 10, we talked of torque. If you remember torque times, it was the force times the perpendicular moment arm. But that perpendicular moment arm, grade 12, you would remember it was the distance from the pivot to where the force was being applied. So we have actually done this. It's just that it was called torque then. Now it is called work done. So we've done this. You would remember that there we were saying it was force measured in newtons and the perpendicular moment arm measured in meters. Newtons, meters. So it was one and the same thing. Okay, so I just wanted to remind you of that we've actually done this, so it shouldn't be difficult. We've done this before, right? But now this formula comes with cos of theta. Okay, this cos of theta is not part of the concept, but part of the calculations. To say you have to take into consideration the angle that will be created between the force in question and the displacement. Okay, this theta represents the angle between the force in question, right? The force in question. This is where it becomes very important to identify those forces, to say, okay, which force is doing the work, or which force do I want the magnitude of the work done from? Okay, that will be your force in question in that case. Now you have to check the angle between that force in question and the displacement. That's where you get how much theta is. A lot of people struggle with this issue of theta. They don't know whether to put 0, they don't know whether to put 90, they don't know whether to put 180. What should I put here in theta? Go and check what is the angle between your force in question and the displacement. It will tell you what your theta should be. Simple as that. For example, if I am pushing, this rock was being pushed and it was being displaced here. If I look, my force in question there will be the 100 kilonewtons, okay? And then what is the angle between the force in question and the displacement? I like to redraw everything. I would say there's my displacement is horizontal like this, and I would say there is my force in question, also horizontal. Between the two, they are parallel to each other. That will mean then the force or the angle between the force in question was what? Was a 0 degrees, okay? If maybe I had frictional forces here, maybe it was on a rough surface and it was moving, the force in question then will be the frictional force, which will be facing in this direction, okay? So here's my displacement facing in this direction. This is delta X. And then here is my force in question facing in this direction. What is the angle between this arrow and this arrow? It is a whole 180 degrees. Now I know what is the theta. What's the angle between the force in question and the displacement? Grade 12, it is important that we must also know that work is a scalar quantity. In mathematics, it is a scalar quantity mathematically because it is a product of two vectors. The product of two vectors will give you no direction mathematically, because if you multiply a positive and a positive, you would get a positive, negative, negative, still get positive. So that's why we say this one is a scalar quantity. So meaning mathematically it will not affect it. However, scientifically it is a scalar quantity because it only has magnitude. There is no direction of work done. You don't say work done in this direction. Why? So let's talk about work done in terms of energy. Work done, grade 12, is just the transfer of energy. It's how much energy was transferred So that is work done. So when we talk work done, we can actually say it is the transfer of energy. And you would remember that energy has no direction. So there is no direction as to the energy went left, went right, or went up or down. Okay, so there's just a transfer of energy. So work is a scalar because it's a transfer of energy, or work is energy. Okay, so energy does not have direction, it only has magnitude. Okay, but another reason could be it is a product of two vectors there. Okay, and the SI unit from that newtons times meter. 1 Newton meter is equivalent to 1 joule. Okay, so the SI unit that we use for energy is joules, grade 12, not Newton meter, even though it will not be wrong, but we use joules for the SI unit. And I would advise that people stick to joules just to avoid any confusions to oneself or to other people who would be checking your work. So let's write joules. Everyone write joules. I was bringing this issue of Newton meter to sort of create this connection between talk that we did in grade 10 and work done that we are doing right now. It's actually the same thing. Okay, right. So let's try and look at an example and see if we will be able to do calculations then of work done. Okay, right. Example 1 there says a block of mass 20 kilograms is pulled to the right by a force of 50 newtons over a distance of 2 meters. So it goes by a force of 50 newtons and it goes over a distance of what? Of 2 meters. Right there, I can tell that there has been a force applied on an object and this object was displaced. Since this object has moved over a distance of 2 meters, it was displaced. That means work was done. But what did the work? It was the forces that were involved in or exerted in that object. The block experiences a frictional force of 10 newtons. So as if you noticed, I said it was the forces. So not one force does work on this object. It's more than one force that is doing work on the object. Right. And then we are asked to calculate the work done by the force applied, the frictional force, and the normal force. Okay. Then they say calculate the work net done. Then they say calculate the work done by the force applied if the block is pulled at an angle of 40 degrees above the horizontal. All right. So let's see as to how we can calculate this. Okay. So the first thing that I would advise that we do then, grade 12, is let's draw the free body diagram so that we can identify the forces that are acting. They said it's a 20 kilogram block. Okay, so let me quickly draw the 20 kilogram block, and it was being pulled by a force of 50 newtons, and then there was a frictional force, I remember, of 20 newtons there. So what we want to do is quickly draw a free body diagram identifying all the forces acting there. So there will be a normal force, okay, then there will be force of gravity. Hope you agree with me there. There will be force applied, and then there will be frictional force. I hope we're all in agreement with my identification of forces. Then they have asked us to calculate the work done by the force applied, the work done by the frictional force, and the work done by the normal force. Where do we go? We've identified the forces that are there. The next step is to go straight to the formula. Go write the formula, substitute in the formula, and try to get our answers. Okay? So we'll say W is equals to F delta X cos of theta. Okay? This is the formula that we were given. So we have to identify all the variables. Do I have the force applied? Because now I'm calculating the work done by the force applied. Do I have the force applied? Is how much is it? It is 50 newtons. Okay, multiplied by the displacement. Oh, I should have indicated the displacement here. It was displaced a distance over 2 meters. So the displacement would be 2. Okay, and cos theta. Now, what is theta in this case? Shouldn't be writing theta here. What is theta in this case? Because now we have to include theta. Theta is an angle. What angle? It is the angle between the displacement and the force in question right now. What is the force in question right now, grade 12? It is the force applied, the 50 newtons. So I have to go back and I have to go and investigate what is the angle between the displacement and the force in question. Let me redraw them. The force in question goes in this direction. The displacement goes in this direction. What is the angle between these two? They are parallel to each other, as you can see. And if you have two things that are parallel to each other, then the angle between them should be 0 degrees. That's how I identify whether it should be 0 or it should be 180. That's where it comes from. So then you go straight to your calculator, open a bracket and say 50 multiplied by 2 cos of 0. At a cos of 0, you should get that the work done is 100 joules. Now, what does this 100 joules indicate, grade 12? It indicates that, so you would remember that if you are pushing something where there's no friction, imagine yourself pushing something on a smooth floor. It will be very, very simple for you to push it. Why? Because nothing works against you. But if you push something on a rough surface, it will be difficult. Why? The friction is working against you. The friction takes some of the energy that you have transferred. So whoever or whatever was transferring these 100 joules of energy into the block, friction was taking 20 joules away from the block. So the 100 was transferred by whoever was applying 50 newtons of force, while the friction was there taking 20 joules away. So this is energy taken away from the system. We call it negative work done. It's called negative work done. So the negative work done is the energy that is transferred away from the system. This is what the negative here indicates. You would remember that work is a scalar quantity. It has no direction. So this negative here does not indicate the direction of the frictional force. No, this negative here is indicating that the energy is being taken away from the system in this case. While there it was positive, it was indicating that the energy is being put into the system. Positive work done on the 100, negative work done on the 20 joules, right? The next question was asking us to determine the work done by the normal force. So again, we'll go to our formula. Work is equals to force delta x cos of theta. Okay, what is the force in question right now? It is the normal force. You would remember that. Let me do it right here. The normal force in this case should be equals to mg. And what is our mass? 20 times 9.8. What's 20 times 9.8? Quickly there, times 9.8. 20 times 9.8 should give us 196 newtons of energy. So our normal force would be 196. Then we can substitute it here as 196. Multiply this by the displacement of the object. The displacement of the object is 2 meters. Cos of what do we put here? Okay, are we putting 0? No, we have to go and investigate. Where is the force in question? The normal force is facing in this direction. Where is the displacement? The displacement is facing in this direction. Now, what is the angle between the displacement and the force in question? It is a whole 90 degrees. So you will put 90 degrees here if you were ever asked that question. So then you put that into your calculator. You should get a 0. Let's confirm that quickly. Cos 90 degrees, not cos 90 degrees. You are going to get 0 joules of work. So that tells us that if the force in question is at 90 degrees to the displacement, then there is no work done. This is the very, very important concept, grade 12. This, what I've just shown you here, is a conceptual question that could be asked, and it could be asked in ways. Okay, so be careful, pay attention to it. If the force in question is at an angle of 90 degrees or is perpendicular to the displacement, then that means no work is done on the object. No work is done if the force is perpendicular to the displacement. A very, very important concept to remember there, grade 12, right? Then the next question, or the last question, was asking, it was not necessarily the last question, but there's a question that is asking us to determine the work net. The work net, the word net means sum. You remember when we were doing F net there. So that means we just simply need to do what? Need to do work net is equals to the work done by the force applied, added to the work done by the frictional force. There will be no need for us to add the work done by the force of gravity and the normal force, because they are going to be zero anyway. They do no work. Okay, so we can just add these two. So work done by force applied was 100 joules, but the work done by the frictional force was a negative 20. So 100 plus a negative 20 should give you what? 80 joules of energy. So the work that ultimately does, or the energy that ultimately does work on this object, this 20 kilogram, is 80. Okay, how did it become 80? Whatever put in the force, let's say the person put in the force, they put in 100 joules. They transferred 100 joules into the block. However, friction took away the 20 joules. And ultimately, we were left with what? 80 joules that did the work. So that's the work net done. There is another way of calculating work net there, grade 12, where you can say work net is equals to F net delta X cos of theta. This one will be more complicated, grade 12. I wouldn't advise people to go through this method here. I would advise that people must calculate the work done separately and do the work net here. But this one would require you to calculate the net force, where you would be adding the 50 with the 20, the 10 newtons, which was the frictional force. It was 10 newtons, right? Then displacement of 2 and the cos of the cos, or the angle between that, which would be the angle between the resultant and the displacement in that case. That's where it could get very, very tricky. So I would advise that people follow this method of calculating. Okay, right. Then the previous question there, or the last question, was asking us to calculate the work done by the force applied, the same force applied, if the block is now pulled at an angle of 40 degrees. Now let's say it is now pulled at an angle of 40 degrees there. Then we are going to say work done is equals to force delta X cos of theta. We keep doing the same thing. The difference is the angle between the displacement and the force in question. That is it, grade 12. Okay, now the force in question now is still same 50, right? But now with a displacement of 2. However, now they are saying it is acting at an angle, meaning it looks like this now. Okay, the 50 is being applied at an angle of 40 degrees. So now, what are we going to say for theta? We can no longer say 0 now. Why? We have to look at the angle between the displacement and the force in question. Where is our displacement? There is our displacement. Where is our force in question? There is our force in question. Are they parallel? No, they are not parallel to each other. Therefore, we cannot say it's a 0 degrees. They have created an angle between each other here. And what is that angle? We are told that it is 40 degrees. Therefore, we are going to substitute what? 40 degrees here. Then we put it there into our calculator. 50 times 2 at the cos of 40. Then you should get that the work done now is 76.60 joules. So the energy that is transferred when you pull at an angle will be less than the energy that is transferred when you pull parallel to the displacement. You would remember that this was also the case in Newton's laws, that when you increase the angle, the net force there will decrease. So this is what is happening here. So most important, grade 12, remember the angle between displacement and the force in question. Remember, positive work done. Remember, negative work done leads you to net work done. Some energy is transferred in, some energy is taken away. We are left with the energy that actually does the work. And then we have, or the work net. Let's not say actually does the work, because they all do the work, but actually does the work. Okay. Then we have, if it happens that your force is perpendicular to displacement, no work is done there. And then that is the one, or the most important things that you need to know when dealing with work done. So here are some of the solutions that have already been worked out there. Grade 12, I'm going to give you 4 minutes to try this activity, and let's see if people are able to calculate work done. Okay, your 4 minutes starts now. Welcome back, Kratos. Welcome back. I hope you were able to finish and you were able to work it out. Now, let's go over the activity. It says there, a man applies a force of 50 newtons. He comes another 50 newtons there to draw water from a well. He lifts 5 kilogram bucket of water from a depth of 4 meters to the top of the well. Okay, so we're going to assume that the 5 kilogram is for both the bucket and the water, because the question is not clear here, but let's assume that for practice purposes. Okay, 5.1.1 says define work done on an object, and 5.1.2 says calculate the net work done on the bucket. Okay, so I want us to just simply check something here. The first examples I showed you was that of an object moving horizontal. Now I'm showing you an object that is moving vertically, because I also want us to discuss that, to say, how do you calculate work done when objects are moving horizontal? Is there actually a change? There is no change or necessarily any necessary change. So let's what we were supposed to actually do then. Great talk. The first answer there is the definition, the product of the applied force on an object and the displacement in the direction of the force. Never mind these lines here. All these words must be there. This is examination guideline stuff. It's either you get it or you don't get it, and everyone must get it. Okay, the product of the applied force or the force applied on an object and the displacement in the direction of the force. All right, and then for us to be able to calculate the work net, we should calculate the work done by the force applied, or let's start by, we should have started by indicating all the forces acting there. So while it is being pulled, we are going to have forces there, the force applied, F applied, and then we are going to have the force of gravity. Okay, don't mind the magnitude of my forces. Okay, so the force applied and the force of gravity. These are the forces that are going to be doing work on this object. We've identified them here. Okay, so there is no frictional force. Okay, let's assuming that no air resistance, and there is none of that. So there are only two forces: the force applied and the force of gravity. So for us to calculate the net work done, we have to calculate the work done by the force applied. And how do we do that? We go to the formula F delta X. Well, it is actually supposed to be delta Y, but no one is going to punish you if you write delta X, because that is the formula given in the sheet, but it's delta Y because we are moving in the vertical motion, cos of theta. Okay, now let's talk about this. Where F is 50 times 4, okay, 4 was the displacement. Cos of, let's look at the angle here, they said 0, okay, and I hope people did not say cos of 90, because if you are saying cos of 90, that means you're still making a mistake. You're still not sure as to what theta means. Theta does not mean a force that faces up will be 90 degrees. Again, we're saying it is the angle between the displacement and the force in question. How is the bucket being displaced? It is being displaced up. The bucket is no longer moving horizontal. It's not being displaced in in grade 10, but probably introduced to you in a different way was the next one in image, where we are talking of the principle of conservation of mechanical energy. Before we can look at the principle of conservation of mechanical energy, we have to revisit this term here, isolated system. Spoke about it at length when we were doing the conservation of linear momentum. We spoke about it at length then. So we said in an isolated system is one on which the net external force acting on the system is 0. You would remember that we spoke about this at length. Okay, so today we're not going to focus on it and say what is it, what do we mean by net external. Okay, we have that even on recording them. So what we are saying today is that for mechanical energy to be conserved as well, it must be on an isolated system, meaning that we take no note of external forces. They may be there, but they must be 0, or they are not there at all. That's why you would find the questions talking about ignore the effect of friction, ignore the effect of air resistance. In this topic, you will find that a lot, because most of the time things are going to be falling here. So ignore the effect of friction, ignore the effect of air resistance, such things. Those will be indicating to you that we want the system, or we want you to treat the system as isolated. We are in an isolated system. Okay, right. Now, before we look at the formulas and the calculation, let's try to understand what do we mean when we talk of state of principle of conservation of mechanical energy. Let's start by stating it. It says the total mechanical energy in an isolated system remains constant. the total mechanical energy in an isolated system remains constant. When asked to state, all of these words must be there. Okay, the ones in brackets are optional. If you want to put them, you can put them. If you don't want, you can forget about them, right? Or you can state it by using the ones in brackets only. The sum of gravitational potential energy and kinetic energy in an isolated system remains constant. Or you can state the whole thing together, right? The total mechanical energy, sum of gravitational potential energy and kinetic energy in an isolated system remains constant. You stated it, but what does it mean, right? Let's talk about what it means. So let's say you have that high building that we were talking about. Here's the high building, very high building there of 20 meters. Okay, let's say that is the height of the building. Okay, right. So in this building, let's say you are having a 5 kg ball just resting on the edge of the building. Just resting on the edge of the building. Okay, that ball, while it is resting there, since it is above the surface of the earth, the ball possesses the energy called gravitational potential energy. So you could be asked to calculate the gravitational potential energy of the ball. Okay, so you would say EP is equals to mgh in calculating that gravitational potential energy. 5 times 9.8 times the height of 20. The gravitational potential energy will be how much? 5 times 9.8 times 20. Okay, 980 joules. It is 980 joules. That's the gravitational potential energy. However, the ball there on top does not have kinetic energy because moving. So if you were to calculate its kinetic energy, EK half mv squared would be half of 5 times 0, because its velocity is 0 since it's not moving, it's resting, which will give you 0 joules. Okay, all right. But now what are we saying about the conservation of linear momentum? We say if the system here is isolated, okay, what will be the mechanical energy of the ball here? The mechanical energy of the ball will be EM or ME is equals to EP plus EK, which will be 980 plus 0. This gives you 980 joules. So the mechanical energy of the ball on top will be 980 joules. Okay. Now, the principle of conservation of mechanical energy says that the mechanical energy of the ball will not change even if the ball starts dropping now. Okay. If the system is isolated, then the mechanical energy or the total mechanical energy will remain constant. So that means the mechanical energy here will be 980 joules, and halfway it will still be 980 joules. And even as it reaches the ground, it will still be 980 joules. It remains constant. The total mechanical energy will not change. The only thing that will change in this case, grade 12, will be the gravitational potential energy and the mechanical energy. Let's talk about it. So let's use a different example to make my math now, right? Let's say the mechanical energy here was 400 joules while the ball was resting. Let's say it's a ball, but the mechanical energy was 400 joules. Okay, that means the EP was also 400 joules. Hope you are following. If the ball is resting, that will mean that the EP was 400 joules. That will mean that the EK was 0 joules while it's resting. I want to do away with 980 to make the math simple. So what is the EK of the ball? The EK of the ball is 0. The EP of the ball is 400. Now, since the EP, the gravitational potential energy, depends on the height, once the ball starts falling, when the ball is somewhere here, the gravitational potential energy of the ball will no longer be 400. It would have decreased to a certain number that we don't know. Okay? And but the kinetic energy would have done what? Would have increased. So when the EP decreases, the EK will do what? Will increase. The kinetic energy increase. You remember that we used to say energy cannot be created nor destroyed. It can only be transferred from one form to another, or converted from one form to another. So what is happening here is that the gravitational potential energy is being converted to being kinetic energy. So the gravitational potential energy will decrease, the kinetic energy will increase. However, the mechanical energy will remain the same. So let's say the gravitational potential energy EP here is now 300 joules. What will be the EK then? It should be 100 joules. 300 plus 100 still gives you 400. Mechanical remains the same. We go halfway here now, halfway of the ground. That means the EP will be what? 200 joules. What will be the EK? It will also be 200 joules. Half of the gravitational potential energy has been given to kinetic energy. What is the mechanical energy? Still 200 plus 200, 400, remains constant. Even as we reach the ground, EP there will then be 0 because there will no longer be height. The EK will be maximum then. It means all of the gravitational potential energy has been transferred to becoming the kinetic energy. The kinetic energy will then be 400 joules in that point. However, the mechanical energy still remains the same, 400 joules. The mechanical energy on top was 400 joules. The mechanical energy at the bottom was 400 joules. The only energies that were changing was gravitational potential energy and kinetic energy. Gravitational potential energy was pouring and giving to kinetic energy. At some point, gravitational energy poured all of its energy and it gave it to what? To kinetic energy. That's the conceptual understanding that at least would say one must understand when it comes to energies here, grade 12. Then with that understanding, you should be able to do the calculations using the formulas. ME at the top is equals to ME at the bottom. It says what the principle is saying. Some people write it as EK plus EP top or even initially is equals to EK plus EP bottom or after or finally. Those are the words that could be used, right? Half mv squared plus mgh. That's when you expand the EK, expand the EP, and then is equals to half mv squared plus EP. One top before or initially, the other one bottom after or finally. Okay, then let's try and look at an example and see if we can be able to do the calculations that we are talking about. They're saying here a rock of mass 10 kilogram resting on the edge of a 50-meter high building suddenly falls to the ground. So it was a rock, it was resting on the edge of a high 50-meter building, and then they say it suddenly falls to the ground. And then they say we must determine the speed with which the rock reaches the ground. They are not even looking for the kinetic energy, they want the what? The speed. But what do we know? We know that the mechanical energy is conserved, okay? Total mechanical energy is conserved in this case, so it should be the same. So we can start and say that ME initially is equals to ME final. That's what I use, initial and final. You can use top and bottom, you can use before and after. And then I know that ME initially is the same as EK, EP, which is MGH initial plus half MV squared initial will be equals to MGH finally plus half MV squared final. That's at the bottom there. I know the mass of the rock to be 10 kilograms. I know this is initially on top, that G will always be 9.8. I know that the height on top was 50 meters plus half of, I know the mass does not change, still 10 kilograms. I know the velocity on top to be 0 since they said that it was resting on the edge. So the velocity should be what? 0 squared equals to the mass of 10 times the G of 9.8. Now, bottom, as it reached the ground, as it was reaching the ground, the height there should be 0 because it is reaching the ground. So be careful there. It's not all the time that the height will be 0. Sometimes they would ask you the velocity 10 meters before it reaches the ground. you should be careful there. Even though we are making an example of 0, it does not mean always it will be 0 there. Even the velocity itself, it does not mean it will always be resting. It might come moving, then it starts falling. Okay, so they're just raising awareness there. Half of 10 times a velocity that is unknown, v squared f. Grade 12. Again, let's do away with this mentality of writing the formula and substituting everything in the formula such that you no longer have an unknown. The formula must always have at least one unknown to say, I am calculating for this or I am looking for this. So let's run away from that mentality. Right, let's take the calculator and say 10 times 9.8 multiplied by 50. That should give us 4,900 joules of energy. This is obviously going to give us 0 because anything multiplied by 0 will be 0. This is equals to, this again gives us 0. Anything multiplied by 0 is 0 times. What is half of 10? That should be 5 v squared f, okay, which is the final velocity then as it reaches the ground. So, and then in solving for this, then we have 4,900, which is equals to 5 v squared f, okay. And then finally, we divide by 5, and we introduce a square root there to get rid of the square there. So we introduce the square root, so it should be 4,900, or the square root of 4,900 over 5. We should get that the velocity will be what? 31.30 meters per second. I would hope that at least you are also you are working with me then to check if you are able to do or answer these questions. So this is how you determine the velocity using of conservation of mechanical energy. There's really nothing more to this. As long as you understand that concept of mechanical energy remains the same, you also understand that the potential energy as an object drops or loses height will decrease, while the kinetic energy in that case will do what? Will increase. Try to understand that, and then you can use the formula to then do the calculations. You can always solve for any unknown in that in those problems. Okay, so that is it for this concept energy. Let's try and move to the last concept. Well, this was the worked out example already, which is the same as what we have worked out together there. Okay, so let's look at the next concept. And the next concept in our 3 concepts that we're looking at today, work, energy, and power, the last concept will be power. We are looking at power now in the context of technology, but the definition would be the same. So you should be able to define power as the rate at which work is done, or the rate at which energy is expended. This simply means transferred or converted. Okay, so this means transferred. Okay, it used to be like that. It used to be transferred. Now they went and used expended. Why? I would not be sure. So, but at the end of the day, the rate at which work is done. I hope you can see that these are connected. All these 3 concepts may be different concepts, but they are connected at the end of the day. Remember, work done, the transfer of energy, right? And then we looked at energy. Okay, now we are looking at the rate at which that energy is transferred, the rate at which the work is done. Okay, how fast do you do work? That's power. Power is not about how heavy you pick things. Here in this concept, at least, it's not specifically about that. And it is all about how fast do you do the work. That's power in science. So we look at how fast, how much time does it take you to do the work. If it takes you less time, then we'd say you have more power. If it takes you more time, then we'd say you have less power. It's all about time. So that's why it is the rate at which work is done. Mathematically, it is written as P is equals to W over delta T, with the SI unit watt. Capital letter W there is the SI unit watt. Okay, right. However, in the context of technology, as I have said, right, the more practical unit of power will be horsepower. This is what you encounter when you're talking cars. Most of the time, cars, the power of cars is not measured in watts. They usually talk of horsepower. Okay, most of the time machinery, they will talk of horsepower. So that's the practical unit, the most or popular unit of power that is used. Therefore, it might not be the SI unit, but it's the more popular one, and it's in the context of technology. Therefore, we must be familiar with it. We should be able to convert between horsepower and watts, and know that 1 horsepower will always be equivalent to 746 watts. So very, very important there, because they will ask you to convert that when you are being asked these questions by the examiner. Right. Then the last point there, and then if we happen to have an object moving at a constant speed, then we can do away with this formula, right? And use the formula which says P average, because then we'll be dealing with average power is equals to force times V average. I've now highlighted this in red because this part in the formula is very, very important, grade 12. So let's do away with writing P is equals to FV and thinking that this is the correct formula. If you write it like this, you are not going to get your mark. They do not accept it being written like this. So let's do away with it and pay attention to the formulas given on your data sheet. It's always going to be PA, standing for average, is equals to